Now, alkynes can also undergo these reactions. If I were to take some general alkyne, in this case I'm going to make it as simple as possible, show that triple bond, and have only an H on one side. If I were to add bromine across an alkyne, assuming that there is excess bromine, in other words, more than enough to make the reaction go, what would you expect this to form? When you think about an alkyne, I want you to be thinking, at least when you're talking about the reactivity, I want you to be thinking about basically two alkenes that are orthogonal to one another. Okay, so you're going to pretend like it's going to react with an alkene. Right? But think about what's happened. We have formed an alkene, and we know that an alkene is going to react with bromine. So there's more bromine there. What's going to happen? It's going to do it again. Now let me clear this up a little bit. It was ugly. Okay, so just to clarify a little bit here, here was the carbon-carbon triple bond bound to an R group, bound to an H. We get breaking of both pi systems and the addition of 2 moles of bromine. Everybody clear on that? Okay. Now, I think we're going to leave alkynes just like that. Now, for alkenes, okay, these are not the only reactions that we're going to talk about. When we come back here on Wednesday, what we're going to start exploring is what happens if I have an alkene that looks like this. Okay, a non-symmetric alkene, an alkene that's bound to 2 different things, but it's not equal. In other words, if I were to react this with some compound XY, which would I expect to form? This, or this. Okay, in other words, which group is going to go where? Now, naturally, in the case of chlorine or bromine, where the 2 atoms are the same, it doesn't matter. But this is going to matter when we start talking about adding water or adding acids across a double bond. Okay, so let's look at an example. Okay, what are the two possible products that could form? Okay, I'll start drawing them here. You start drawing them in your book. Are these the same possibilities you came up with? Okay, so we can either add the HCl across the double bond where the H goes to the more substituted side of the alkene, in other words, the side that has the two CH3s, or we can set it up so that the hydrogen goes to the less substituted of the two carbons of the alkene. What do you think happens? Which one do we make? You get votes for the first one. How many think it's the first one? How many think it's the second one? How many think it's both? How many abstain? Okay. At least you're being honest. I appreciate that. It turns out that this is the product that is favored. Heavily favored. I mean, I'm not talking like, 55-45. I'm talking like 90-10, 95-5. Very much favored. This is what we call the Markovnikov product. Okay, the other one is the anti-Markovnikov product. Now, do I expect you to spell Markovnikov? No. I'm not going to ask you to spell it. Okay. Of course, we do have to give credit where credit's due, and Markovnikov's the guy who kind of summed this up. Markovnikov's product arises due to Markovnikov's rule. Which, when paraphrased, equates to the rich get richer and the poor get poorer. In other words, the side that has the most hydrogens is going to get the hydrogen. The side that's rich in hydrogens is going to be richer in hydrogens. And the side that's poorer in hydrogens, well, it's going to be even more poor in hydrogen. So how does that work here? Well, if I were to look at my alkene that I'm starting with and examine the two sides that I could react with, this carbon or this carbon, which is the more substituted carbon? Blue or green? Blue. Okay, which one has more hydrogens? Green. So which one's richer in hydrogen? Green. So the new hydrogen is going to be attached to the green carbon. Now, in the last 3 minutes, let me say this. Markovnikov's rule is a learning mnemonic. It's not like the molecule sits there and goes, all right, two carbons start arguing with each other. Who gets the hydrogen? No, I've already got hydrogens. Give me. There has to be some kind of physical reason for it. And there's a very physical reason for it. Next class we're going to explore this, but this reaction involves the formation of carbocations. And do me a favor, before you come to class on Wednesday, either open your textbook or go to Wikipedia or just do a Google search for carbocation. And please just read for 10 minutes about carbocations. Okay, the more versed you are in carbocations when you come in here on Wednesday, the easier it's going to be for you to comprehend what's happening in these reactions. All right? You folks go have a good evening, and I'll see you on Wednesday.